All right, hello everybody. Welcome back from lunch. We have another session coming up. First speaker is Vivien, who's going to tell us about verifying implementations of differential privacy. Go ahead, Vivien.
Cool. Awesome. All right. So, hey everyone, and thanks for attending this talk. So we're going to talk about verified differential privacy today. And I just want to preface this by saying that at the time of this research, we were all at Boston University. I was finishing my undergrad, and Arthur was a postdoc. Since then, I've moved on to software engineering at a firm in Austin, Texas. And Arthur is now an assistant professor at RIT, which is very exciting. Okay, cool. So just to give everyone a brief overview of what we're going to talk about, I'm going to spend a lot of time on motivation. And specifically, I'm actually going to describe a bug in an implementation of differential privacy. Okay, and then I'm going to move on to our results. And there are really two sections for this. The first one is approximate privacy. And this is going to be something called alpha prime differential privacy. And then we're going to move on to showing exact privacy. And this is alpha differential privacy. Then I'm just going to finish up with some future work that we're considering. Okay, so we all know that data can be very valuable, specifically to researchers, but it's also very sensitive. Okay, and so if I wanted to publicly share this information with the public, or maybe some faculty at a university, that might be a little bit precarious. So the point of differential privacy is to give us a way of sharing sensitive statistical data while still protecting the privacy of the individuals that are in this data set. Okay, so for example, the US Census Bureau does this to provide statistics about the US population, and Apple and Amazon and many other companies have adopted this method of obfuscating data. So an intuitive way to do this, right, is going to be to draw noise from some probability distribution and add it to a query result that you have. Right? This will give you some obfuscation of the original data that you have. And this is exactly what Cynthia Dwork proposed in her formalization of differential privacy. Now, the underlying distribution that she used to do this was the continuous Laplacian distribution. Okay? So obviously, to implement this kind of mechanism, right, we have to sample from this actual probability distribution. Now, the process that many people choose to do this is something called inverse transform sampling. And it's very simple. It's a two-step process. In the first step, what we're going to do is we're going to sample from a uniform distribution about 0, 1. And then we're going to pick the first value of the cumulative distribution function that's greater or equal, okay, to the value we sampled from our uniform distribution. Okay, so going forward, I'm going to use some vocabulary. And it's very important that we establish what I mean when I say these things now. So I'm going to say ideal distribution a lot. This is going to be the actual underlying probability distribution that we use in our formalization. Okay, and then I'm going to say implementation a lot. And this is the probability distribution that's generated from the sampling routine. And as we'll see, this is actually only an approximation of our ideal distribution. Okay? So here's a hypothetical scenario where we have a continuous distribution, right, formalized over real numbers, okay? And in this case, right, where we have infinite precisions, if we think about how inverse transform sampling works, and we pick some p, some probability value from the interval 0, 1, let's say that it's this one that corresponds to 1 on the CDF. Well, in this case, right, this sampling is actually exact. Mainly, if we can sample every single point of this ideal distribution, then our implementation and our ideal distribution are identical. Okay, so this is great, but there's a problem here, and that is that there's no infinite precision on finite machines, right? We can't do this. So when many people went to implement these mechanisms using inverse transform sampling, what they did was they substituted the real number arithmetic for floating point arithmetic. Now, the result of this is what we see below, where our wonderful continuous distribution basically becomes discrete because we had to truncate all the real numbers, right? Okay. So now intuitively, right, if we were going to sample this distribution exactly, our uniform distribution would have to have every single possible double in the interval 0, 1, right? Now, it turns out that this isn't the case at all. And if we do overlay a uniform distribution, a hypothetical uniform distribution, we see that we might actually have a scenario like this, right? Where we have a mismatch in the probabilities of our ideal distribution and those of our uniform distribution. So in this case, right, we can see that the ideal distribution is not the same as the implementation. Okay, so to understand why this actually matters, right, we need to understand what differential privacy is in a more formal manner. So as I said before, right, it's basically this function that takes in a query result, adds some noise to the query result, and outputs, right, the result of that addition, right? So fairly simple. So our goal really here is to make two neighboring queries indistinguishable from one another. And what I mean by neighboring here is that if Q was 10, then Q prime might be 9, or it might be 11. Basically, these queries are one apart, okay? So intuitively, right, there's some probability that running this mechanism on a given query will give you some output. And so for neighboring queries, if these were really indistinguishable, well, then this ratio of probabilities would be exactly 1, right? And so this is actually an indication of perfect privacy, right? These queries really are indistinguishable. Now, the smaller alpha gets here, right, the worse the privacy becomes, right? Because these probabilities are farther apart. Okay, now just a quick footnote for people. A lot of people are familiar with epsilon delta differential privacy or epsilon differential privacy. Now in our formalization, we use alpha differential privacy. And the reason for this is because it's very important for us to have a rational number. So it's just a convenient form to express the privacy guarantee of the mechanism that we'll use in the future. If you want to think about this in terms of epsilon differential privacy, alpha can be expressed as e to the minus epsilon. It's the same thing. Okay, great. So as I said before, the ideal distribution is not identical to our implementation. And the consequence of that is that the implementation really can't guarantee the same privacy guarantee as our ideal distribution did, right? Now, the mismatch in probabilities is obviously of concern, but there's actually something that's even worse, right? So if I just added this horrible red point right here, well, if we think about inverse transform sampling, right, and we pick this value of the uniform distribution, well, then we're always going to sample this first point, and we're never going to be able to sample this red point. Okay, so what does this mean? Well, it means that our implementation, right, actually has probability 0 of sampling that point. What does this mean? Well, we have no privacy now, right? If you think of that ratio, right, if we consider these two neighboring queries, well, the numerator now might be 0. Okay? So this is a disaster, and we want to avoid this at all costs, right? Now, luckily, there is a solution, and the solution is to use discrete probability distributions implemented using rational numbers to avoid truncation entirely, okay? Another thing that we're going to do here is we're actually going to sample from a discrete uniform distribution. It's going to be of size t, okay? And the support is going to be the numbers from 1 over t all the way till 1, okay? Now, this solution has a lot of promise, but we need to be very careful, okay? Mainly about two things. First, that the uniform distribution has to be big enough. Why? Well, because we still might have this situation where we can't sample every single probability from the ideal distribution, okay? And the second thing is that our implementation is still an approximation, okay, of the ideal distribution. All right, so I'm going to go through our formalization in a few steps, and I'm going to start by talking about our implementation of the geometric truncated mechanism. Now, I haven't introduced the geometric truncated mechanism yet, but this is our ideal distribution, okay, in our formalization. So two things that I want to say about this, right? Obviously, to actually formalize something like this, we need two things. The first is finite probability theory, okay? And then for this, we're going to use a library called FinProb. This was actually developed by Arthur at BU, okay? So it proved very useful for our implementation. And the second thing is we're going to need rational arithmetic. And for this, we use the rat data type and the corresponding theorems implemented in SSReflect. Okay, so the geometric truncated mechanism has a couple of parameters. Mainly, we have alpha, which is in the interval 0, 1. Okay, and then we also have a parameter n. Now, it's a good idea to think of n as the size of your database. And the reason for this is because, as we'll see, right? The geometric truncated mechanism is going to truncate all query results greater than n back to n. Okay, so if you don't want to lose accuracy in your query results, it would be a good idea to set this parameter to the the maximal query that you could actually obtain from your database. Finally, we obviously need a query, and then we have a given output, which is really just a possible result of the mechanism. Okay, so on the left here, we have a two-sided geometric distribution, and on the right, we have the probability mass function of the geometric truncated mechanism. And so the important thing to grasp here, right, is that if you look past n, you'll see that all the probabilities are 0. And if you look to the left, right, past 0, well, then you'll see that those probabilities are 0. And so the intuition here is that the support of this distribution is the set from 0 to n. Okay? Now, I omitted a lot of the code that we wrote because really the sampling routine is all happening in one place here. So if you take a look at this function geometric truncated mechanism, it has type nat to prob nat. Now here prob nat is the type of finite probability distributions. Okay, and mainly to implement this, we use a primitive from the FinProb library called sample. Now conceptually, what this is doing is it's sampling from one distribution and it's outputting another, okay? So in our case, right, as I described inverse sampling, inverse transform sampling, right, we're drawing noise from this uniform distribution, we're sampling a probability from it, and then we're outputting this new distribution, okay, where Dirac is another primitive, right, and this is really just giving us the point mass function of our distribution. Now here, find, right, is basically returning the first index of this CDF vector, okay? And the CDF vector here is just the cumulative sum of the PMF, okay? But find is returning the first index for which our predicate here holds true, okay? So this is literally just doing inverse transform sampling. Cool, okay, so that's our implementation of the GTM. And now I'm gonna move on to talking about the minimum size that we need our uniform distribution to have. Okay, so once again, we have this horrible situation that we need to avoid at all costs, to have some privacy in our implementation. And so proving this theorem, which basically says that the support of our implementation is exactly 0 to n, is enough to give us some privacy. So let's think about why this is the case. Well, basically what this is saying is that for every single point in our ideal distribution, there's a value in the uniform distribution that can sample it, okay? Now let's think about what needs to be true for this to happen. Well, all values of the ideal distribution have to be greater than 1 over t, okay? Right. So there's two reasons for this. The first one is, if you remember, our uniform distribution has values 1 over t all the way up to 1. So if we had any probabilities that were less than 1 over t, well, we wouldn't be able to sample them using inverse transform sampling. Now, the other reason that we must have this, okay, is because, if you'll remember, the CDF is the cumulative sum, okay, of the PMF. And so therefore, if you can guarantee that every point of the CDF is at least 1 over t apart, well, then you can guarantee that a distribution of size t is going to sample it, right? Now, when you do this proof and you break it all down, it's a lot of lines of proof, but what you'll find is that the size of the distribution has to be this number 1 plus alpha over 1 minus alpha to the n. Now, an important note here, alpha is irrational, so this number is very big. And if you observe this number, what you'll find is that it gets smaller as alpha arbitrarily approaches 1. Okay, all right, great. So that helps us with this horrible situation. So now at least we have some privacy, okay? But our approximation is still a problem. And for this, we want to quantify a new privacy guarantee that this approximate implementation can uphold. Okay. So the main issue here really is that picking t naively leaves us in a place where we can't guarantee that our implementation is identical to our ideal distribution, right? Now, luckily, what we can do is we can quantify the bound that separates our ideal distribution and our implementation. Now, you can read this theorem if you want, but the key piece of information coming out of this is that the probability values from our ideal distribution and our implementation are at most one step of the uniform distribution apart. Okay? Now, this is great because it allows us to reduce the possible ratios of our implementation's neighboring probabilities to a worst case, right? So if you can imagine, right, that the probability from our implementation of, inputting Q and getting some output is a certain thing, right? Well, then really, we can express this we can express this using the probability from our ideal distribution because of the bound before. So the worst possible ratio we could have is if our ideal the implementation's probability in the numerator was the ideal distribution minus one step of the uniform distribution, and in the denominator it was the ideal distribution plus one step. Okay, so now all we have to do is find the neighboring probabilities of our ideal distribution that give us the smallest alpha prime, and it turns out that these are D and D prime here. All right, so intuitively, right, if you look at the form with alpha prime, as t approaches infinity, right, we're basically going to get alpha. Okay, so this is a graph, and as you can see, right, when t is very small, we have pretty bad privacy loss, but as we increase the size of t, the privacy loss isn't that bad. Now, the utility of this is that we can always quantify the privacy loss that we have with any t that we pick. Now, just as a reminder, right, I slapped this big bold line in the middle because we do need a minimum t to have some privacy. Okay. All right, great. So now we have a quantification of our privacy loss and a privacy guarantee for a naively implemented mechanism. Okay. But we still want our implementation to be identical to this ideal distribution. Okay? So mainly what we need to do is get a situation like the one below, where the sample probabilities are exactly the same as those of the ideal distribution. Okay? Now this isn't actually too difficult to do, because if we observe the ideal distribution, what we're going to see is that all the values are multiples of alpha. Okay? So this means that there must be a common divisor, and this common divisor has to be the smallest of the probabilities, right, of our GTM. So if we suppose that alpha is some number a over b, and we plug that into this smallest probability, what we'll find is that this common divisor, right, is b to the n times b plus a. Now, let's make things even simpler for ourselves and suppose that alpha is always of the form 1 over b. Well, then t will have to be b plus 1 times b to the n. Okay, this is going to be the form for b. Now, doing this is going to preserve alpha differential privacy, which was the initial privacy guarantee that we had for this formalization using the ideal distribution. And this is great, right? This is the best privacy guarantee that we can hope to have for the geometric truncated mechanism. Okay, now there is still a problem here. And that's that the common denominator rate, this common divisor of our ideal distribution is huge. So suppose that your database had 100,000 rows in it, and you set alpha to 1/3, right? And then correspondingly, you have to set t to 4 times 3 to the 100,000, right? That doesn't seem like it's very practical in terms of efficiency of your implementation. So there's a few ways that you can actually address this. The first one is to use a smaller n. Now, what this is going to do is it's going to cause you to lose some accuracy in your results. And the reason for this is because, as I mentioned before, this mechanism has support 0 to n. So any query that's greater than n, we're just going to map right back to that interval. Okay. The second thing we could do is we could use our quantification of privacy loss, mainly alpha prime differential privacy, to pick a smaller t where that observed privacy loss isn't that bad, right? Maybe we're okay with, having an alpha of 1/3 instead of 1/2. We can pick a corresponding t that lets us do that. Okay, so I was interested in the efficiency of this implementation, so I wrote one in Python. And just an example here. If the size of your database was 10,000, you set alpha to 1/3, and then t is correspondingly 4 times 3 to the 10,000. Well, then the running time for a query is about 0.35 seconds in this case. Okay? Now, of course, this is going to grow exponentially as we increase n. But what I will say about this is that really the bottleneck of this sampling routine isn't necessarily sampling from a large uniform distribution, but it's more that you have to build this CDF vector. Okay? And the computation for that, especially using rational arithmetic, is very expensive. So you can imagine that every time you run this mechanism, you have to build this list of 10,000, of size 10,000, and that's very expensive. So that's the majority of the running time here. Okay. All right, so that now we have exact differential privacy, which is great. Okay, that's exactly what we wanted. And I'm going to move on to future work. So I think one thing that we could do that's pretty low-hanging fruit would be extraction to OCaml, and then probably release this so people could use this implementation. I think that could definitely be useful. Now, something else that I think is pretty interesting is verifying the accuracy of the mechanism. And I haven't touched on what accuracy of a differentially private algorithm is, but basically, right, if you consider the difference, right, between the input to this algorithm and the output that you get, well, then you want to make sure that the probability of that being greater than some constant is limited, right? And so just to give you an example of a mechanism that I can think of right now that would be perfectly private, what if we just used a uniform distribution? Well, then we would have an alpha of 1 for sure, but there would be absolutely no utility in something like that because it's basically just this pseudo random number generator that outputs garbage and preserves none of the patterns in your data. So you don't want that. And so the accuracy is actually a pretty big concern when we're talking about these implementations. So another thing that we could do would be to verify a C implementation using the verified software toolchain, which was developed at Princeton and allows you to do proofs over the abstract syntax trees of C programs. So I think that this could be pretty nice, specifically because I think that when this original formalization by Cynthia Dvork was done, there were 4 implementations of differential privacy that were kind of targeted for industrial use, and they all made this mistake of truncating the real numbers when they used floating point arithmetic. So I think that verifying a C implementation and then releasing that could definitely be useful. And then the last thing would be to verify a constant time algorithm that was suggested by Victor Balser and Salil Vedant. Now this has 2 points of interest. The first is obviously that it might help with the efficiency of this algorithm. Obviously, this depends on what the actual constant time is. Maybe it's really bad. But the second thing is that actually has implications for the security or the privacy preservation. The reason is because if you imagine that you have this implementation running and you're a covert actor, right? You could actually observe the running time of the mechanism. And then based on that, start to discover some information about what the original query that was passed into the implementation is. So yeah, I think that all these possibilities are interesting, but I would definitely be happy to hear from the audience on what they think is valuable or if they have any other ideas. But with that, I think I'll pass it on to questions.
So when you say we want to verify a constant time algorithm, do you want to verify the correctness or also that it's constant time?
That's a great question. So when I put this on the slide, I was definitely thinking just the correctness in terms of alpha differential privacy, but certainly the verification of it being constant time can be very interesting because of this attack that I described.
Tiny follow-up question. Are you aware of methods of proving that something, an algorithm is a constant time one from
Ah.
Coq, or?
I am not, but I believe that the next talk is about, or there's one talk about complexity analysis. So
Lovely.
yeah, I think that'll be helpful. We have a question over here.
Hi, I'm Scott from University of Chicago. When you mentioned that all the other implementations do this fatal flaw with truncation, do you think that there's any hope that in some sense you could verify that certain properties about double truncation is safe under this model? Or do you think that doubles are just such an odd way of visualizing rational numbers that it's just hopelessly lost?
Right. So I believe that the implementation that Ilya Morinov proposed when he found this exploit actually does produce every single double, between 0 and 1, every possible floating point. So I think that that actually is possible, but I believe that the accuracy of that mechanism wasn't great. So I think it's probably better to go with something like this. Certainly easier to verify, I would think.
Hi, I'm Lisa from Northeastern, and I just wanted to know, have you looked at all into or is there any work on how prevalent this kind of attack is? Like you're saying that in theory, right, this issue exists in all of them, but it's possible that they're not actually running into that problem.
Right. So yeah, I mean, I think that what you're essentially getting at is whether someone has actually tried to get at the original query result using this attack. So I'm not sure, but I don't think so, because I don't think anyone knew about the existence of this until Ilya Morinov published the paper that showed that this actually happens. But someone might know better than me on that front. So I'm not entirely sure.
Okay, thanks.
Yeah.
Any other questions? Okay, let's thank the speaker again.